We'll continue our discussion on optical receivers. And so first, let's briefly discuss some electronic circuitry that is used after the photo detection, right? So we discussed last time there are two main types of photo detectors used, which are like the pin photo detector and the avalanche photo detector APD. Right. So once this photo detection has converted the incoming optical signal into an electrical current out, right? Typically, we do some further electronic processing before sort of we can recover the bit stream, right? That was transmitted. So let's just sort of briefly discuss some of that. So again, so you have your photodiode here. It could be pin or APD. Your optical signal coming in, right? So this is some data on it, right? Right. So there is, we saw that typically you have to apply some reverse bias voltage to operate the photo detector. So, and then here we have a photocurrent coming out, right? Which sort of looks like this, but like could have a lot of noise and, you know, so just the raw current coming out, maybe sort of too noisy, and there might be too much intersymbol interference going on to straight away recover our bit stream. Okay. So typically you have some additional circuitry after the photo detector. So immediately after, you could have what is known as a pre-amplifier. So this is an electronic amplifier, okay, which amplifies the current. Okay. So this part, like the photo detector with this pre-amplifier, is known as the front end of the receiver. Okay, and then after this, you have what is known as the linear channel, and here we basically do some filtering to remove basically this noise. Okay, and improve your signal to noise ratio. So in this linear channel, you could have another amplifier here to let's say further boost the signal, or let's say these two together have some different frequency ranges for amplification. So this is sometimes known as the main amplifier. And then you have some electronic filter here. It could be an analog filter, or it could be like a digital filter based on DSP chips. Okay, so that's the second sort of part of the receiver, known as the linear channel. And then finally, after this, so hopefully now, like here, your current or voltage, somewhere here you might have also converted your signal from current to voltage, but it doesn't matter, it could be current or voltage. Now, hopefully after doing all this, now your bit stream looks sort of much better. Okay, and then finally, you have the data recovery portion. And so here, so for example, what you can do is, so you set a threshold and you say, okay, so you set a threshold and then you have a sampling time. So, okay, so first thing you do is clock recovery. Okay, so you recover the bit period, right? And then you sample every bit period. Right, so this is dB here, right? Okay, and then depending on whether your sample is above this threshold that you set, if it's above, you say, okay, it's bit 1. If it's below, then you say, okay, it's bit 0. Okay, so after this, basically, you recovered your bit stream. Okay, so and then finally the metric of how well your receiver and also your overall link is operating is now you check how many errors you have in this bit stream compared to what was sent at the transmitter. Okay? So-called bit error rate. So maybe let's just briefly discuss some of these components. Of course, there's a lot of electronic design that goes into each of these components. Right? So we won't go into a lot of detail, but we'll discuss some important characteristics. So if I look at the front end here, the preamplifier used. So there are two main types of preamplifiers that are typically used. Okay, one is a high impedance amplifier. So in cases where your incoming signal here is very weak, okay, that you actually need a lot of gain to get an appreciable signal. In that case, you use what is known as high impedance or high gain amplifier. Okay, so typically it looks like this. So we have a photocurrent coming out of the photodetector here, so which I can represent by a current source. Okay. Then typically I have some load resistance in parallel, and there is some capacitance of the circuit here also, which includes the device capacitance here, which we had discussed. Because so you have a reverse bias PN junction, so it has its own capacitance here, plus the capacitance of the electronic circuitry here. Okay, and then you have some amplifier circuit like for example, op-amp circuits or something, where you amplify the signal to get some V out. Okay. So this is your what is known as high gain or high impedance amplifier. Okay, so if you look at the transfer function for this kind of circuit, right? I can if I define this V out by the photocurrent input as a function of frequency, right? So I can treat this as an impedance which is a function of frequency, right? And so it's in parallel with this load resistance, so you can and so for example, you can assume an ideal op-amp such that the current input here is 0. So you can find out what you can relate V out to IP easily just by simple KCL, KVL, right? So what you get is okay. So equivalently, I can write it like this. Okay. So the transfer function looks like that. So again, for example, if you plot the magnitude of this, it looks something like this. With increasing frequency, the magnitude is going down, right? And the cutoff frequency here is something like given by this product of the load resistance times the total capacitance, right? So this bandwidth here, delta F, um, right, is given by the product of this, and the peak gain here for low frequencies is G times R, right? So basically here what we do is, typically for this kind of circuit, RL is large, okay, so typically greater than like a kilo ohm or so. Okay. So you can get very large gain within the bandwidth of the amplifier. Okay, but that also you can see limits the bandwidth here. Okay, so this kind of circuit works well when your data rate is not too high, but if the incoming signal is very weak. Okay. So this total capacitance here is typically the sum of the device, the photodiode capacitance, plus the capacitance of this amplifier circuit. Okay. So, okay. So yeah. So this kind of amplifier is used for weak signals when your data rates are not too high. Right? So basically, you want your bit rate to be less than the bandwidth of the amplifier to not distort the signal. The other type of amplifier, if you are working at high bit rates, so you want a high bandwidth amplifier, is what is known as a transimpedance amplifier. Okay, so there what you do is you, instead of putting the load resistance slide across your photodiode, you transfer the load resistance to across your op-amp gain circuit. Okay, so okay. So you can do a similar analysis here. So now the current coming here goes into this load resistance, right? The current into the op-amp is 0. But anyway, you can again simply calculate just from KCL KVL the relationship between V out and IP. So now you get okay. So now basically the gain of this op-amp here comes here in the denominator with the RC. Okay. So it goes away from the numerator here and it comes here in the denominator with the frequency. Okay, so now again, so now basically now because you've divided this RC by this factor G, right, which would be large for op-amp circuit, So and again, so if you plot the frequency response, like the cutoff frequency would be now given by RL3T by G, right? So or this will be G divided by 2 pi RLC. Okay, so basically effectively you increase the bandwidth by a factor of G, right? The price you pay is that the gain, you can see that the peak gain goes down by a factor of G, right? The peak gain here is now proportional to RL, but the bandwidth has now increased by a factor of G. Okay, so so this is for weak signals, and this is for high speed or high bandwidth signals. Okay. So because you get lower gain with this one, typically you have to have another amplifier maybe after this to even further boost the signal. But if you're using a high gain amplifier here, many times you don't need this second amplifier in the linear. Okay. So of course I've drawn very simple circuits here. If you look at an actual receiver that is made, like a lot of additional complications they do here to sort of minimize the noise and just improve the circuit performance in general. So yeah, that's a matter of electronic circuit design, which is sort of out of the scope of our course. But sort of the general idea is discussed here. Okay, so that's the front end. Now for the linear channel, basically the main part is this filter. Okay, so right out of the photodiode, right, you have this noise on the signal. Then you use an amplifier. So basically now your noise is also amplified. So typically, like if you look here, you have boosted your signal, but your noise is also amplified. So the SNR is not great. Okay, so then typically to get rid of this sort of high frequency noise, you have to use some kind of filter here. So there's a question, a combination of both amplifiers used together. Yeah, so one can also try to design like a combination of these two amplifiers as a single amplifier. But you can see that for any amplifier you design, there's a limited bandwidth and gain, right? So sometimes what is done is like, for the first amplifier, you have some bandwidth over which you amplify, and then you take the remaining frequency range and then have another amplifier which amplifies over that frequency range. Because sometimes it can be difficult to just design one amplifier which works over a wide frequency range with a high gain. So, but yeah, you can try to design something then. Okay, so yeah, so let's look at this filter. Okay, so I mean, essentially what you want is some kind of low pass filter, right? Because the noise is typically higher frequency than the bit rate, right? So the idea is, so basically convert your sort of voltage or current with respect to time from this kind of waveform to something now which is right, like has a higher SNR. So yeah, basically in frequency, the frequency response that you want is some kind of a low pass filter. Okay, but just any kind of low pass filter might not work, because so when you're cutting out the high frequency components, right, that's like stretching the signal in time, right? So basically what you might do is you might worsen this intersymbol interference that is happening, right? Because if you cut out these high frequencies basically and only have the low frequencies present, then in time domain you're sort of stretching out the bits, right? And you might make the this extinction between 0 and 1 even worse, leading to even more intersymbol interference. Okay. So this filter needs to be designed carefully. So if you look at so if I call the voltage after the filter here V out, okay, then V out of omega I can write as some transfer function which is an impedance times the photocurrent here. Okay. So this impedance of course includes all this, the pre-amplifier, main amplifier and the filter. Right, I'm going from IP to here. So this one typically will be sort of like the input impedance to the front-end amplifier here times the gain of these amplifiers here times the filter response function of this filter. Okay, so we saw, for example, we saw G of omega, what it looks like for a couple of these amplifier designs, right? So now basically want to have some form for this H of omega, HF of omega for the filter response, such that this V out of omega or equivalent time domain, I can write the time domain signal here, V out T, as a convolution of some impulse response for this part of the circuit. Right, where basically the ZT, small zt of t is the Fourier transform of this capital ZT of omega. Right. So it's sometimes easier to analyze a normalized version of this equation. So what we do is normalize by the DC values. So let's define, for example, okay, like that, normalize by the DC value. Similarly, for the photocurrent, okay, so then I can write this equation as some normalized output spectrum, which is a product of some transfer function times the spectrum of the normalized spectrum of the photocurrent. right? So this is the right. So this basically depends on the bit stream that is received here, right, along with the noise added on, and this is the output. The spectrum of the output signal here, which we then send to the decision circuit, right? And this is the response of all the components in between. Okay. So typically, what we do is we design the amplifier, the net bandwidths of the amplifiers here, to be larger than the filter bandwidth. Okay. So, if this is the filter bandwidth here, typically the amplifier bandwidth will be so this GP and GA. So that typically will have a larger bandwidth than the filter. Okay. So this H total, HT, is a product of this H filter times the amplifier, right? So the product of these two will be primarily determined by the filter only, because the filter has a lower bandwidth, so that determines the cutoff. Okay, so under that approximation, this I can just say mostly it's just the filter, but for a to model the performance of the receiver completely, you have to of course take the full response of the amplifier and the filter. But for now, let's assume that the filter typically has lower bandwidth than the amplifier. Okay, so what we are saying here in a sense is that the output waveform that I get finally here, right? So this is some H out of T, and its spectrum is H out of omega, right? That is given by the filter response function times my photocurrent spectrum, right? And the photocurrent is just basically my incoming bit stream, right? So what kind of waveform do I finally want here, so that I can send it to this decision circuit and then recover my bit stream properly, right? What I want is a good extinction between the neighboring bits, right? So that you can distinguish the neighboring bits as 1 and 0. So that's another way of saying you want to minimize the intersymbol interference, right? So one kind of waveform that is popularly used here, okay, is what is known as a raised cosine filter. So this f of omega looks something like this. Okay, this is, so again, it's a low pass filter and it goes to 0 at the bit rate. Okay, so of course you could have many different low pass filters which have this property of going to 0, right, with different shapes here. But the one popular shape which is used is known as a raised cosine filter, okay, where this h of omega for, we write it as a function of the actual frequency f in hertz. Okay, so it's like 1 plus cosine of pi f by b. That's why it's called a raised cosine. It's like a cosine plus a DC. Okay, and then 0 beyond b. So you can imagine like something like this is optimum, because if you design a filter with a lower bandwidth, right, that will broaden out your signals more and then lead to sort of intersymbol interference. If you have a filter with higher bandwidth, then basically you're letting more noise in, and the signal to noise ratio will be worse. Okay, so the optimum it turns out to be somewhere where you cut off at the bit rate. Okay? And people have done a lot of research, and after that they found that if you have this raised cosine shape, that sort of gives you sort of like the optimum pulse shapes here, that now my decision circuit can work. Okay, so if you have this kind of response in the frequency domain, sorry, this is not the filter. Let me go back. So this is the output spectrum, right? So this is the output waveform, and this is the output spectrum corresponding to that waveform. Okay. So we'll work backwards from this and then find out what should be this filter response that we want here. Okay, so right now we are here just at the output waveform. So output waveform, so if you look at this in the time domain, so you take the inverse or the Fourier transform of this, you get h out of t . Okay, so basically what I'm saying is that the final waveform that I'm sending to for my data recovery has frequencies only up to the bit rate, right? So it has information about my data up to the bit rate, but then it's 0 beyond, so it has no noise at frequencies above the bit rate. Okay, that's what this means. And the output waveform has a spectrum like this, which means that there is no power in the signal beyond a frequency of the bit rate. Right, which means that you can see here this waveform will look quite smooth. Right, there are no fluctuations here faster than the bit rate. So okay, so if, yeah, so what this h out of t is what I'm talking about here, right? So if you plot this, this looks like so if you plot this waveform here, it looks something like this. So it's going to 0 at 1 over b or TB, right? And also minus. So you have sine of 2 pi b times t. So if t is 1 or 1 plus minus 1 over b, then this is sine of 2 pi, which is 0. Okay, so you get a pulse shape like this, right, which has an extent from sort of between minus TB to TB. So now if I shift this and look at the next bit, that looks like that. Similarly on this side, right? So now basically if you look at some sort of eye pattern which is formed, right? So that looks like this. Okay, and basically what you ensured is that, right, this thing goes to 0. So there is no contribution from the neighboring bit to the voltage of your current bit, right? So if I'm looking at the voltage, and basically I'm sampling here in the middle of the bit period, this over here. So if I look at this current bit here, that is the pulse I'm getting, and there is no contribution from the neighboring bits because that is 0 at my sampling time. Right, so this one is also 0 here, and this one is also 0. Okay, so this kind of waveform ensures that you have no interference from the neighboring bit if you are sampling at the center of the bit period. Okay, and you get sort of like a nice open eye. Right, and now you can do your decision threshold. You can have a threshold somewhere in between, and you can say, okay, if my sampled voltage is higher than threshold, I say 1 and 0. Okay. So, if you design your filter such that your output spectrum looks like that, this raised cosine form, then that ensures that your time domain pulse looks like that, which has a nice open eye, and with good fidelity you can decide whether your bit is 0 or not. Okay. So if you want this kind of pulse at the output given by this kind of spectrum, right? So this is what we want here at the output. We can sort of assume that this bit stream coming here at the input, okay, is some like nice bit stream like that, right? So let's say like rectangular pulses. Of course, you know that because of dispersion, etc., the pulses coming here won't be nice and rectangular. But again, there are a lot of dispersion compensation techniques that we have discussed, right? So let's say we use some of the dispersion compensation techniques to compensate for the dispersion and then sort of recover the transmitted pulse quite well here. So let's assume that's the case. So then this photocurrent spectrum will be the Fourier transform of this bit stream. Right, so again, so if this is bit period TB here, and you have a rectangular pulse of that duration, then this HP of omega or HP of F, you know, so the Fourier transform of a rectangular is a sinc function, right? So here you have sin pi f by b divided by pi by b, right? Where b is 1 over TB. Right, so that's my input spectrum coming here. And this is the output spectrum that I want here before I send it to my decision circuit. So which means that my filter response, right, has to be basically this divided by this. Right? So this one, you know, is something like this. Right, so basically the filter response I want is this divided by that. So yeah, this function divided by, right, so if you just do that and use standard trigonometric formula. So here I assume that this HP of T is basically rect of T by TV. Right, so the filter function here would be H out. Right, so this is basically output divided by input. So you can see this comes out to be a quat or cotangent function. Okay, so that's the filter, this filter function that I want, a cotangent function. So again, if you plot this, this looks like a low pass filter, of course. Okay. And of course, zero beyond this. Okay, so basically all this discussion was to say that the shape of this low pass filter that you want here is optimum if that shape is a cotangent function. Okay, so if you use such a filter, basically you get a nice data stream like this with a good open eye here that you can now sample and recover your stream. Okay, so yeah, that's all I wanted to discuss about some receiver circuitry. Now we can go on and discuss basically these noise mechanisms. So what is this noise which is getting added onto the signal? So we had discussed one such mechanism when we were discussing transmitter, right? So the laser output itself will have some noise, which we call the relative intensity noise. But we'll see that basically the major noise is actually added here at the receiver itself. So let's discuss that. If there are no questions on this part. Right, so basically as you go along this receiver blocks here, you're successfully or serially reducing the bandwidth as you go further and further. Right, so the photo detector has to have the maximum bandwidth so that it detects all the variations well. Then your amplifiers will have some cutoff frequency, so they'll remove some frequencies. Then your filter will remove some more frequencies. So as you go along the depth of the circuit here, your bandwidths are getting smaller and smaller, and then finally you end up with just the bandwidth of the bit rate. Okay, so let's discuss the noise mechanisms introduced at the receiver, which is basically the major noise sources. If you look at your optical link in totality, the major noise is actually introduced at the receiver. Okay, so we'll see. So this is the major noise mechanism, and then other noise, as we saw, it could be added at the transmitter itself from the laser, and then if you have amplifiers along the fiber channel, then the amplifiers will also add that noise. Okay, but the major noise typically is from the receiver itself. Okay, so imagine you have some optical signal here coming in, right? Then this photodetector is giving you a photocurrent out. So imagine that your input, so the light here is a constant power, a constant intensity, right? With absolutely no fluctuations. Okay, of course, this is not perfectly true, we saw, right? For LEDs, these fluctuations can be quite big, right? Few percent typically. For lasers, these are much smaller, but still not zero. Typically, for lasers, they might be less than 1%, like 0.1% or something. But let's ignore that for the moment. Let's say this is constant. Okay, even then, if you look at the photocurrent coming out, that will have some fluctuations. Okay? It won't be perfectly smooth like your input optical power. Okay, so if you look at the average current here, right? So this IP will be a function of time, even though if this is constant. So if I look at the average of my photocurrent with respect to time, that is the responsivity times the optical power here, right? But there is some variance. Okay, so if I look at the total photocurrent, that is a mean photocurrent here, this mean, which is this responsivity times the mean optical power, plus these fluctuations, which are typically two sources for these fluctuations. Okay, so one is called short noise, and the other is called thermal noise. Okay, so if you look at the average, so now if I take the average photocurrent here, that's just IP, or the responsivity times the average optical power, which means basically the average of these short noise and thermal noise is 0. Right, so sometimes you have positive fluctuation, sometimes you have negative fluctuation, but the average is 0. And typically if you plot let's say you keep sampling and see, you plot the magnitude of the fluctuation. So you plot, for example, IS or IT, right? And the number of times that fluctuation occurs. So this is some kind of frequency, density function, right? So you'll see that you get some kind of Gaussian function like this, right? So most of the time there is no fluctuation. Sometimes there is a fluctuation to the positive side, sometimes to the negative side, right? But the probability of a fluctuation with higher magnitude goes down. And typically you can fit this with the Gaussian function. Okay. So this is something like the probability of having a fluctuation with magnitude this IS of this current. Okay, so these sources are what are known as Gaussian noise sources, which typically most noise sources are have these Gaussian statistics. Okay, but if you look at, so again from this probability function, you can see that if you calculate the mean, that is 0, right? So this is like Gaussian function with mean 0, but there is a variance, right? So basically, if you look at the average of the square of the noise current, that is not 0, right? Because square is always positive. So when you average that, you won't get 0, right? So basically, this is the variance. So let's discuss both of these sort of one by one. So if I look at short noise, so we had briefly sort of discussed about short noise when we were discussing the laser intensity noise, right? So there we were saying at especially high frequencies, the relative intensity noise reaches a level which is given by the short noise, right? And that is basically due to the discrete nature of photons. Similarly here, this photocurrent which is generated is basically carried by individual electrons, right, which are flowing. So it's not that you can continuously break down the charge to smaller and smaller values. Finally, they're being carried by individual electric charge of certain unit, right? So basically, you have these discrete units flowing, which are collectively giving you a current. And again, like for example, if I have some way to measure how many electrons are passing through in a given time interval, that will be randomly fluctuating. Okay, even for a given DC current, if you look at the number of electrons passing through per time interval, that will be fluctuating. Okay, so it's no way for me to say when the next electron will come. Okay, and that's just again from fundamental quantum mechanical fluctuations. Whenever you have some discrete particles moving through, you have this uncertainty, right, or probability. So the question is, both short noise and thermal noise need not have the same variance. Yes. So these two need not be equal. I mean, they won't be equal with. Yeah. So you're correct. But I mean, I just wanted to say that they are non-zero. But yeah, they are not equal to each other. We'll see. Okay. So again, the same reason that because your electric current is being carried by discrete units called electrons, automatically you, because of that, of the fluctuation in the number of electrons passing through at any given time interval, you have this short noise. Okay. So again, short noise comes from fundamental quantum mechanics, and if you look at again, so if I try to measure, let's say some delta T and see how many electrons are passing through per this delta T, right? And if I just measure that for many times, I will get some distribution like this. Okay, so if n is the number of electrons that I measure in this time interval, and so this is the number of times I measure that, or the probability of getting n electrons in this time interval, it will have some function like this, which is given by what is known as the Poissonian distribution. Okay. Same is also with photons. So at the transmitter, if you're looking at short noise, then if you're looking at how many photons are being emitted per unit time interval, that will also have some distribution like this, same Poisson distribution. Okay. So because we are looking at discrete values, right? So n is an integer here, 0, 1, 2, 3, 4, 5, 6. So that's why it's a Poisson distribution. But when your average is large, so when the average value of n here is very large, much greater than 1, which typically you'll have for any practical amount of photocurrents that you're using, for example, in telecom link or something, right? So, for example, let's say you have microwatts or milliwatt of optical power, you get microamps or milliamps of current. Those correspond to many millions and billions of huge number of electrons per unit time. So this n here is very large, okay, and in that large n limit, this is well approximated by Gaussian. Okay, so for n much bigger than 1, this is it's very well approximated by Gaussian. That's why under most practical conditions you see a Gaussian probability. Okay, but if n was very small, okay, if you are working with a few quanta, then basically you will see the deviation and you will see that a Poissonian function is the better. So in some case where you will be working with very few quanta, then maybe we will briefly take a look at that maybe in the next class or a couple of classes from now. Okay, but in the usual case, the number of particles are so much that this is well approximated by continuous Gaussian. Okay, so but again, so how do we characterize the noise? So I have some fluctuating waveform here, right? So this is T and this is Is of T. Sometimes I get a positive fluctuation, sometimes I get a negative one. So the way to characterize this is take the autocorrelation function, right? So you find this autocorrelation function, which is, so you have measure this for a certain time, then you shift this waveform by some time interval tau, multiply by the two waveforms, and then take average of it. Right? This we discussed already when we were discussing the relative intensity. So that's the usual way to characterize any type of noise. So you find this autocorrelation function to tell me what is the correlation time, right? What is the time over which these fluctuations are correlated. So if you do that for short noise, turns out actually it's a delta function. Okay, and its magnitude is proportional to the average current. Okay, so yeah, so there is some average current here. I should draw this lower here. Right, so I'm getting some average photocurrent here, IP, and then there are fluctuations above and below that. So this will be the total current. So the IS will be this, right? Right. So now, if you look at the autocorrelation function, you get a delta function whose magnitude is given by the average photocurrent. Okay. So if I have a larger average photocurrent, then these fluctuations are also more. Okay. Where that is coming from is again this Poissonian statistic. So you know for a Poisson distribution, I don't know if you recall, but if the mean, if you have a mean here, the standard deviation of the Poissonian distribution is given by the square root of the mean. Okay, and the mean here is basically the average photocurrent, right? So as you increase the mean, your standard deviation is also going up. Okay, so it's a square root. So now this correlation function is the product of the two it's a product of two currents, so it's like I square. So that's why that is proportional to IP. Each of this is proportional to square root of IP from here. Okay, so this coming fundamentally from the underlying Poissonian statistics. So the correlation function looks like a delta function with magnitude equal to the average photocurrent times the electronic charge. Right. So again, this Q is coming because each electron carries a charge Q. Okay, so this is that. And now you know that if I want to know the frequency content of this noise, the so-called noise power spectral density, then I take the Fourier transform. Right, so I get the short noise power spectral density by taking the Fourier transform. The Fourier transform, the delta function, you know, is just a constant function. So it's just a constant with magnitude QIP as a function of frequency. It's time. Right, so a delta function means that this is totally uncorrelated noise, which means that if you have a fluctuation at a particular time, the next time instant, that fluctuation is totally uncorrelated to the previous fluctuation. So each fluctuation is independent. That's what this means. Okay, so right, and now again, depending on the bandwidth of your device, right, the noise within that detector bandwidth, if you integrate this noise power spectral density within the detector bandwidth, then that is the total amount of noise that you will see. Right? So basically, what we are saying is that the total noise, so variance, average of I square, you can see from here that's just the correlation function at zero delay. Okay, that is just the integral of the power spectral density. Okay, so typically, so when we just do this, we get what is known as a two-sided power spectral density with both negative and positive frequencies. Usually, we want to talk about like only positive frequencies. So what we do is we just double this and then keep only the positive frequency. Okay, so we say that the power spectral density is 2 times QIP and only consider F greater than 0. So that's known as the one-sided power spectral density. Okay, so then the total noise current variance here will be just the integral from 0 to the detector bandwidth delta F of this one-sided power spectral density. Right, and for short noise, it's just a constant, so it's just straightforward. This is just 2 times QIP times delta F. Okay, so the short noise current variance is proportional to the average photocurrent that I get, which is proportional to the average optical power and my detector bandwidth. So you can see short noise is what is known as a multiplicative noise. Okay, it's so usually you might have heard in communication systems about additive noises, right? Like additive white Gaussian noise is something you might have heard about. So that means that basically the noise, so your signal, then the noise is independent and just gets added on to the signal. Okay, but here you can see that the noise is actually dependent on the signal also. Okay, So this is a multiplicative noise in the sense that here it depends on the magnitude of the signal, right? So it's getting multiplied by some by the signal magnitude. So short noise is not an additive noise. So now if we see the thermal noise, okay, that we'll see is an additive noise. But anyway, I hope so. That's about short noise, and sometimes we include another factor here. So remember, we discussed that there could be a dark current also from my photodetector. So even if I don't have any optical power incident, just due to the internal noises within the device, there could be some small dark current which is flowing. So if you include the dark current also, that will also have its own short noise. So sometimes we also include that to write this as, so the mean photocurrent plus the dark current times that. Okay. So for example, like if you have simple OOK modulation, then the IP for bit 1 typically will be much higher than the dark current. But for bit 0, IP will be close to 0, so then dark current might be important. Okay. So now let's discuss thermal noise. Okay, so thermal noise, as the name suggests, it's from thermal fluctuations within my electronic devices, right? So you have this randomly, so thermally generated electrons which are randomly flowing through my device. Okay, so typically, if I connect some load resistance here, right? So there are some thermally generated electrons which are flowing through my resistor. Okay, so sometimes it's also known as noise. You might have heard the term Johnson, named after the person who first. Or sometimes it's also called Nyquist noise. Okay, so again, same procedure. So you have these fluctuations. You take the autocorrelation function. Right. So now the autocorrelation function is not a delta function, but a very sharply peaked function. It's not a pure delta function anymore. The width of this line here is somewhat dependent on temperature, but typically it's less than. So the if I call the width here some tau c, the tau c is less than like a picosecond. Okay, so this is quite narrow. So there is some correlation for very short time scales, like less than a picosecond. So tens of femtosecond, 100 femtosecond. Over that time scales, the fluctuations are correlated, right? Because these are electrons which are flowing physically, right? So you can imagine that they can't flow faster than a particular velocity, right? So for very short time scales, the fluctuations are correlated. But anyway, so when you take now again the Fourier transform, so now you get some frequency spectrum like that. Okay, and the frequency extent in of the power spectral density will be sort of inversely proportional to this correlation time. Okay, so for 1 picosecond, this roughly corresponds to about 1 terahertz here. So this goes up to like roughly 1 terahertz. Okay, and the value here depends on temperature. Okay, again, so we do the same thing that we convert the double-sided to a single-sided. So we multiply by a factor of 2. Okay, the peak value here comes out to be 4 kVt by RL. Okay, so it depends on temperature and the load resistance. Okay, so you can see that so it's inversely proportional to the load resistance. So if you have a high resistance here, then the electrons find it harder to flow through. Right? So the current will be lower, and it's directly proportional to temperature. So as you increase temperature, the electrons have more thermal energy, so they can move faster or give a larger current. Right. So and again, if I want to find out the total noise current variance, I just integrate this up to my detector bandwidth. Right, and typically detector bandwidths are close to the bit rates we are operating at, right? And the bit rates we are operating at typically like are tens of gigabits per second, maybe up to 100 gigabit per second, right? So those frequencies are much smaller than 1 terahertz. So in that frequency range, we can almost assume this to be a flat line. Okay? So we can assume this to be white, although it is not white, it has a frequency dependence. Short noise we saw was completely white, right? So white means that all frequencies are equally present. But here it's not, the thermal is not exactly white, but for if our frequency range of operation is much below this cutoff, then we can approximate it by the white noise. Okay, so then basically we can write this as the power spectral density times now again the detector bandwidth. Right, so this delta F is the detector bandwidth, which is much less than 1 over tau c. Okay, so if I take RL to the other side, right? So I square RL is something like the power dissipated, right, in the resistor here, and that is you can see is equal to kVt, which is like the thermal energy, right? kVt, you know, is a unit of thermal energy times delta F, right? So kVt has units of energy, right? F is 1 over time, so this is power. I square R, right? I square R, and this is also power. So it's like the thermal energy that the electrons gain is being dissipated in the resistor here. Okay, so typically we also include an extra factor with this, okay, which is the amplifier noise figure. Again, so we had discussed that typically after this, like for example, we might have some amplifiers, right, some front-end amplifiers, pre-amplifiers or something for post-processing the signal, right? And so these amplifiers will also worsen my noise, right? So these amplifiers will have their own electronic circuitry, they will have their own thermal fluctuations, okay, which will sort of add on to these fluctuations that I'm getting here. So to take that into account, we multiply by this factor, which is like a noise figure of the receiver circuit. Okay, so if all you had was just the load resistance and you're just measuring the voltage across it, then you just have this. But as we discussed, we typically have some additional circuitry after this, right? And so to take that into account, we multiply by this factor. So this factor is obviously larger than 1. Okay, so these noise figures are typically measured in dB. So for example, 6 dB means that the noise is enhanced by a factor of 4. Okay, so the total current variance, like the total variance in the photocurrent that I get here, so right. So if I look at IP's, the variance of the current, or this will be that is the sum of the short noise current variance plus the thermal noise variance. So that I can write like this. Okay, so that's the total variance in the current, or basically the noise that I get here. Okay, so it depends on the bandwidth of my receiver and these other factors. Okay, so now you can see this will limit my signal to noise ratio, right? Because this is acting as a noise and I have some signal level. So there is some finite signal to noise ratio. And basically, if you want to recover our data with as few errors as possible, then we want the SNR to be high, right? So that we can distinguish the bits easily. So we can do this separately now for the pin and the APD, because we'll see that the noise will act slightly differently in both cases. So if we first look at the pin photoreceiver, right, the SNR is basically the average signal power, right, which is the average currents. So the signal I'm getting, so here I'm talking about the electronic signal, right? So this will be the average, right, divided by the average noise power. So this will be this variance times RL, right? So this will be IP squared divided by right. So the SNR in the electrical domain, right now I've got my data back in the electrical domain. So the SNR that I have now in the electrical domain is the square of the mean photocurrent divided by the variance. Right. So now we know this is just responsivity times average optical power. And then for the variance, we can put this. And now IP here, again, we put responsivity times average optical power, right? Okay, so thermal noise here you can see is independent of the photocurrent or independent of the optical power. So it just adds on to my signal, right? It's not proportional to my signal. It's some constant value which gets added. So the thermal noise is additive, whereas the short noise is multiplicative. Okay, so typically for pin photodiodes, we know that so this responsivity typically is like for example near 1 amp per watt or something, right? So it turns out that the short noise current variance is typically much smaller. So if you take temperature to be near room temperature, 300 Kelvin, and typical load resistance is, let's say, like 50 ohm to 1 kilo ohm in that range, then typically this thermal noise is much larger than this short noise. Okay. So typically at room temperature, pin detectors operate in what is known as the thermal noise limit. That is basically your thermal noise current is much bigger than the short noise. Okay, so for the typical optical powers used, let's say up to a milliwatt, around a milliwatt or so, at room temperature, this term is much bigger than this term for responsibility around. Okay, so in that case, if you neglect this term, then you can see that in the thermal noise limit, the SNR comes out to be okay. So in the thermal noise limit, you can see that the SNR is directly proportional to my load resistance, right? Proportional to square of the optical current or optical power, or the square of the photocurrent, and then inversely proportional to this detector bandwidth. Okay, so again, you can see that I want as small a detector bandwidth as possible without distorting my signal, so my SNR is high. So in the thermal noise limit, basically, I can just improve my SNR by using a larger load resistance, but again, recall load resistance also typically affects my delta. Okay, so then there is this term, so for pin detectors operating in the thermal noise limit, which is typically the case, there is this quantity defined which is known as noise equivalent power, NEP. Okay, so if you pick up any commercial photo detector, if you look at the data sheet or the spec sheet for the detector, it will quote an NEP value. Okay, so this is basically the optical power required per unit bandwidth to get SNR equal to 1. Okay, so you can see here that the SNR is directly proportional to the square of the optical power, right? So as I reduce my optical powers, my SNR is going down. So there is a minimum optical power here, which will give me an SNR of 1, right? So that is the noise equivalent power. And then we normalize it with the bandwidth, because there's a delta F here, right? So this is basically P optical divided by square root of delta F. Okay, we take all the other terms on this side. So we put this equal to 1, and then take all the other terms to this side, and we are left with P square by delta F. We take the square root of that, we get P by square root of delta F. Okay, so that is the noise equivalent power. So the units you can see are watts per root hertz, right? So typical, if you look at typically the detectors which are used for telecom, the pin photoreceivers. Typically, their NEPs will be somewhere in 1 to 10 picowatt per root hertz. Okay, so you can see it just depends on the temperature of operation, load resistance, responsivity of the detector, and the noise speed. Okay. So it's a property of my receiver. Right, so it gives me an idea of what is the minimum optical power that it can detect, right? Because if your power is below this, then the SNR is below 1, which means you cannot distinguish it from noise. Right? So basically what you do is you take the NEP for that detector, then multiply by the square root of the bandwidth of your receiver to get the total noise power, right? And that is the minimum optical power that your receiver can detect. There is also another term sometimes it is used, which is called detectivity, which is equal to 1 over NEP. Right? So for a good detector, you want a low NEP, right? You want to be able to detect low powers. So you want a low NEP or equivalently high detectivity.